We are discussing about GATE 1994 ECE paper, and the topic we are discussing is electron devices. This is 7th 1 mark question, came in GATE 1994. It is related to match the following question related with respect to BJT. First we will see on the left hand side. Left hand side there are three options, and right hand side there are 5 possibilities. We must match left hand with right hand side. First left hand side are A. The current gain of BJT will be increased. B. The current gain of a BJT will be reduced. C. The breakdown voltage of a BJT will be reduced. Options on right hand side. 1. If the collector doping concentration is increased. 2. If the base width is reduced. 3. If the emitter doping concentration to base doping concentration ratio is reduced. 4. The base doping concentration is increased, keeping the ratio of the emitter doping concentration to base doping concentration is constant. 5th. The collector doping concentration is reduced. We must match the left hand side with right hand side. But the thing is, all are related to the BJT, and that too all are related to the current gain and breakdown voltage. Simply the BJT in active region, if we discuss, at that time we can able to answer all these things. So we will discuss now BJT operation as amplifier. So we are concentrating on these three things with the help of BJT operation. So simple NPN transistor we are taking in common base configuration. Base is common for both input side emitter base junction as well as output side collector base junction. We know that when BJT can be operated either as a switch or as amplifier or oscillator. So if BJT has to work as amplifier or oscillator, at that time it must be biased in active region. The meaning of active region is emitter base junction forward bias, collector base junction reverse bias. So we must use power supplies such that power supplies and possibly current limiting resistors, such that we must get the condition of emitter base junction forward bias, collector base junction reverse bias. This process is called as biasing. Biasing is the process of keeping the transistor in active region with the help of external voltages and current limiting resistors. So here VBE and VCB are going to be chosen such that emitter base junction is forward bias, collector base junction is reverse bias. Look at this one. Negative terminal is connecting towards N side of the emitter. That is nothing but JE is forward bias, emitter base junction is forward bias. JC, collector base junction, will get reverse bias if you apply positive potential of the battery towards N side, that is collector side. Normally the transistor operation is nothing but simply output current is approximately equal to input current, that is collector current is approximately equal to emitter current. IC is almost equal to IE, even though the collector base junction is reverse bias. If you are looking at isolated junctions, if the junction is forward bias, a large current flows. If the junction is reverse bias, a very small current flows, that is very small, such that nanoamperes in case of silicon and microamperes in case of germanium. That is very small, that can be neglected. But here if you look at collector base junction is reverse bias, but the current flowing through this junction is equal to IC, which is approximately equal to IE, that is the current of forward bias junction. So under reverse bias we are getting a maximum current, that is the current which is equal to forward bias current. How this is possible? This is possible only with respect to base. Base has two important characteristics. Because of that one, transistor operation as amplifier is possible. Otherwise transistor operation as amplifier is not possible. that is making IC approximately equal to IE is not possible if these two conditions doesn't met. First condition is base is lightly doped. Compared to emitter and collector, base is lightly doped. That is what it is shown on the diagram also. N plus plus P and N plus. N plus plus emitter is heavily doped. N plus collector is moderately doped. P, there is no plus sign, that is lightly doped. So lightly doped base, moderately doped collector and heavily doped emitter. Second characteristic of base is base width is very thin. Base width is very thin is nothing but base width is very small, such that the recombinations present in the base is going to be reduces. The recombinations taking place in the base will reduce. We will see the operation. Whenever this emitter base junction is forward bias, at that time electrons from emitter are going to be repelled by this negative terminal. So the electrons are repelled by this negative terminal and holes from base are repelled by this positive terminal. So that holes are moving in this direction and electrons are moving in this direction. So that electrons will enter from emitter to base, whereas holes will enter from base to emitter. And conventional current direction is same as hole current direction. So as the holes are moving from right to left, emitter current direction is taken out. Okay, that's why this is the reason why we are going for the symbol of NPN transistor, which arrow goes out. That arrow implies whenever emitter base junction is forward bias, that arrow specifies the conventional current direction. And whenever the electrons are coming into P side, at that time the electrons will become minority carriers in P-type base and they will try to recombine with the holes present in that P-type base. So because base is lightly doped, there will be less number of recombinations taking place and the leftover electrons are going towards collector side. So these leftover electrons are going to be collected by this positive terminal to get a large current. Because collector base junction is reverse bias, by that time no current is flows due to the majority carriers of collector and base. But these are the electrons, even though they look like majority carriers, they are not belongs to the collector, they are coming from the emitter. So a large number of electrons are coming from the emitter to collector and that are collected by this positive terminal. By that time those electrons forming a closed loop that gives rise to a large current. If the number of recombinations in the base is very small, at that time maximum number of electrons from the emitter will reach the collector. That is nothing but IC will be approximately equal to IE. So if you make base width very thin, by that time the current ratio, that is IC to IE ratio, will be increases. So this is first important point. If base width is going to be reduces, if base doping concentration reduces, number of recombinations taking place less, so that current ratio IC by IE increases. Second point second point is nothing but if the base width is going to be very thin, at that time also the number of recombinations are going to be taking less. Practically the width of base is going to be much lesser than the diffusion length of minority carriers in base. That's why we generally says WB for NPN transistor is going to be far less compared to Ln. Ln is nothing but diffusion length of electrons in P-type base. So the width of base should be chosen such that the width is going to be very smaller than the diffusion length, so that whatever we expect small number of recombinations because of lightly doped, even that are not going to be taking place. The number of recombinations will be still lesser than the expected value because width of base is very thin. So that again the current ratio is going to be increases because maximum number of electrons are reaching from emitter to collector. So these are the two possibilities how the current ratio is going to be increases. First one is by reducing the doping concentration of base, and second case is nothing but by reducing the width of base. There are third possibility also. That third possibility will explain with this equation. Total emitter current is consisting of both with respect to electrons which are going from emitter to base, and with respect to holes which are coming from the base to emitter. So IE, total emitter current, is sum of IEN plus IEP, that is emitter current due to electrons plus emitter current due to holes. But emitter current due to holes is no way related to the collector current. Have you observed this one? The holes are going to moving from base to emitter. Nothing is going towards collector side to contribute for the collector current. So collector current is no way related to the hole current of NPN transistor. So that is the reason why the base must be very lightly doped and very thin, so that this hole current is going to be very, very small. So total emitter current is going to be dominated by the electron current, that is nothing but emitter itself, concentration of emitter itself. So IE is equal to IEN plus IEP. So IEN plus IEP is approximately equal to IEN. Sorry, this is make small change. It is IEN plus IEP is equal to IEN. This is okay. Make correction. This is IEN, which is approximately equal to IC. So IC will be more. If IEN by IE has to be more, by the time IEN should be more than IEP. That implies nothing but emitter doping concentration to base doping concentration, IEN with respect to IEP, if you compare, this is related to the current related to the emitter doping concentration, this is related to the base doping concentration in case of NPN transistor. So if you look at this equation, IEN by IE, that is nothing but IEN by IEN plus IEP. So if IEN is very, very large compared to IEP, then IEP can be neglected. This ratio will be equal to 1. So IE is equal to maximum, and that is equal to IC. So IC will be IE if IEN by IE is very large. Are you understanding the situation? That implies nothing but if you increase the ratio of emitter doping concentration to base doping concentration is increased, by that time also current ratio increases, IC will be more. Okay. So from this one we can go for the three important statements. Current gain can be increased with respect to base, either by decreasing the base width, or by reducing base doping concentration, or by increasing emitter to base doping concentration ratio. If the emitter to base doping concentration is constant, at that time there will be no change in the IC. Remember that one. If the ratio is going to be constant, emitter to base doping concentration ratio is constant, then no increase in the collector current is possible. Next, how to reduce current ratio? Exactly opposite. Again we are going for the same equations. IE is equal to IEN plus IEP, which is approximately equal to IEN. Again it is, I copied the same thing, so this must be IEN. Okay, please make sure it is IEN. Next, current gain can be reduced with the same thing, either by increasing base width. If base width increases, number of recombinations taking place increases, so that collector current reduces because base current is increasing. And next, by increasing base doping concentration. If you increase the base doping concentration, at that time more recombinations taking place in the base, so that less number of electrons are reaching the collector side, so collector current is going to reduces. That is, current ratio IC by IE is going to be gets reduced. Next, by reducing emitter to base doping concentration ratio. So that is, if you are reducing IEN to IEP ratio, at that time you cannot neglect IEP from this equation, so IC will be much less. So these are the possibilities of reducing the current gain. Next possibility, next thing is nothing but we are discussing about the power dissipation, that is breakdown voltage, how it will be reduced. Okay, answer for this give answer for this question. Power dissipation in active region of a transistor, it will be more across emitter base junction or collector base junction. Power dissipation, will it be more at emitter base junction or collector base junction? The answer is power dissipation is more at collector base junction, because normally power dissipation is nothing but current into voltage. If you observe, current is going to be in emitter base junction, the current flowing is IE, in collector base junction the current flowing is IC. So IE is approximately equal to IC. IE is approximately equal to IC. So at both junctions current is almost same. What changes the power dissipation is nothing but voltage. Across forward bias emitter base junction, the voltage will be around cut-in voltage. If it is silicon, VBE will be almost around 0.7 volts. In collector base junction, the junction is going to be under reverse bias. Under reverse bias, total applied voltage will be taken care of diode itself, reverse bias diode. So if you apply large reverse bias, the total voltage will be drop across reverse bias diode. Now reverse bias diode has higher voltage than forward bias junction, so that power dissipation across emitter base junction is IE into VEB, VEB is 0.7 volts, whereas power dissipation across collector base junction is IC into VCB, VCB is very large. So power dissipation across collector base junction is going to be large. So whenever we say power dissipation, at that time it is related to the collector base junction, that is IC into VCB, or we can say IC into VCE. Both are almost same, just only differed by 0.7 volts. So generally power dissipation across a PN junction is calculated with the help of current flowing through the PN junction and voltage across that PN junction, that is I into V. For a given power dissipation, that is if the power dissipation is going to be a constant one, for a given power dissipation, voltage reduces, I increases. If the current increases, to get the same power dissipation, voltage is going to be gets reduced. It's usual. Current increasing is nothing but doping concentration increases. That is, by increasing the doping concentration, power dissipation, that is nothing but the given power dissipation occurs for smaller values of voltage across diode. This is the reason why Zener breakdown occurs at lower breakdown voltages, whereas avalanche breakdown occurs at higher voltages. If you observe, Zener breakdown occurs in heavily doped PN junctions. In heavily doped PN junctions, the current components are going to be very large. Currents flowing through the junctions are very large, so that breakdown occurs at smaller voltages, around less than 6 volts. Whereas avalanche breakdown is lightly doped PN junction, so that current flowing through it is small, so avalanche breakdown taking place at larger reverse voltages. So we can conclude, for the given power dissipation, to get the fixed power dissipation, if you increase current, by that time voltage across that one reduces. So we will apply this one for our transistor, so that we can make one conclusion. For a transistor, power dissipation is more at collector base junction than emitter base junction, just now we have seen. So if collector doping concentration increases across collector base junction, if collector doping concentration increases, then breakdown occurs for smaller reverse voltage of VCE for given power dissipation, that is breakdown voltage reduces. So breakdown voltage reduces if collector doping concentration is increases. Now with the help of this theory, we can answer the questions. This is first one, current gain of a BJT will be increased if A gives rise to second one, if the base width is reduced. current gain of a BJT will be increased if the base width is reduced. Current gain of a BJT will be reduced if the emitter doping concentration to base doping concentration ratio is reduced. And C, the breakdown voltage of a BJT will be reduced if collector doping concentration is increased. So these are the right options: A matching with 2, B matching with 3, C matching with 1. Thank you.